Roger, go for deploy.
Welcome to the podcast.
Welcome.
Welcome to the show.
You're gonna have a sick time tonight.
Welcome to the podcast.
I felt I was a little bit flat there.
Adventure Fit Radio.
Welcome, everybody.
How's it going, everyone?
Yeah, really good.
So today we have the G-Man, Geraint Lewis. Nah, it is Geraint.
It's Geraint.
No, we were saying Geraint as in Geraint, but it's actually Geraint.
Are you 100%?
Yeah, I think
What did he
so.
say?
He said Geraint, I'm
Did he
sure.
actually?
Yeah. So you'll notice in this podcast, guys, we absolutely love this guy. We
love him.
He is our first big science guest that we've had.
Yep.
And he blew our faces apart in Sydney. We did an hour with him. And then we also we wanted more content, so we came home and we recorded on Skype. That'll be part 2 of this two-part show. So the first one's in person, the second one's in Skype. But the problem is, his name is spelled Geraint. So we were like, oh, can't wait to interview Geraint Lewis.
Yeah, Geraint Lewis.
Geraint Lewis. Yeah. But then he told us that he's Welsh, and that's not actually how you pronounce his name. It's, well, Tommy thinks it's
I
Geraint.
still can't even remember.
But no, because we thought Geraint and it was Geraint, but it's actually
Geraint.
Geraint.
So it's not Geraint.
No, it's Geraint Lewis.
So, like we said at the start, guys, we just ended up calling him G-Man. It's just so much easier.
It was much easier to just be G-Man.
Yeah.
So the show itself, it was
So
Tommy's
good.
favourite episode when we walked out. I was frustrated because it was right at the end of our Sydney trip. We had to run off to the airport, whereas because we just crammed so many shows in there, so we actually had to put it on ice. But I said, no, we're not releasing that. That didn't do it either of us justice. So we had the second Skype, and we finished off with our 6 from 6, which we didn't get in the first one.
It's good.
This is the first episode, and this is basically about the Big Bang and how the universe was created.
Yep.
Basically all it's about.
Black holes.
And it was sick. So
good.
hope you really like it. We are sponsored by Audible. So, guys, if you want a free audio book and a 30-day trial for Audible, which we both highly recommend, go to www.audibletrial.com/ADVF radio. By the time this is released, I'm not sure what I'll be reading.
Yeah.
But I have a bunch of stuff in my wish list. I've got Sapiens, which is about the evolution of mankind. Guns, Germs and Steel, which is basically about the history of the world. I've got the Elon Musk bio in there that I'm looking forward to.
That's in mine.
Really looking forward to that one. I've got Hitchhiker's Guide to the Galaxy for a day when I just want a little bit of light-hearted sci-fi.
Good little book.
So I love it. I literally love Audible, guys. So I think you will too. So if you want to check it out, head to audibletrial.com/ADVF radio.
And it's so much easier for people that, want the good content, but don't really enjoy reading, It's just listen to it, exactly like Bill said, when you got a bit of time, driving from point A to point B, as opposed to hearing all the shit that's on the actual radio. It's so much better.
Fuck the radio.
Fuck the radio. We are also
not Adventure Radio, of course.
Not Adventure Radio. Not us.
We love Adventure Radio.
Hey, Bill, who else are we sponsored by?
We are sponsored by Adventure Fit Travel. So, guys, we are... What are we doing? I'm trying to think of when this is going to be released. So, Adventure Fit Travel, guys. So, basically, we are an adventure travel company for the fitness community. We do all kinds of cool stuff. We've been to New Zealand and trained with Richie Patterson, who's about to... he's a 3-time Olympian just now. He's over in Rio. We also train with CrossFit Games athletes there. We've trained with world champion weightlifter Dimitri Klokov in Bali. We've been through Japan. World-class gymnasts. We had coaches over there. We've done lots of cool stuff. We've got the Philippines coming up in November. Dimitri Klokov is involved again. Got to get on that one because tickets are selling fast. Pretty much, that's pretty much it. It's really cool. If you haven't already, check it out, www.adventuretravel.com.
Excellente.
Excellente. Here's the show. Okay, guys. Here we are with Geraint Lewis. Did I pronounce that right?
You did.
Geraint Lewis. Me and Tommy all day have been saying we got to get to Geraint.
Yes.
But we've been wrong.
Do you know what we could do in like whenever we get this wrong, you just say not Geraint, not Geraint. That's what I'm going to do from now on.
All right. Here and to start us off, as usual, we've got a tribute to Geraint. Tommy's tribute.
Beautiful. Welcome, my friend. Put together a little something here, basically of what Bill and I want to get out of the show. So hopefully you can give it to us. chase education. We want to know about creation. And Bill and I think you can help us on our quest for knowledge. And I cannot wait for Geraint to take us back to college. I definitely screwed the name up. Damn. Sorry, mate. I had one job. Not Geraint.
Oh, what a classic.
Damn.
Beautifully done.
Yeah. Thank you, mate.
So, Geraint, welcome to the show.
You just call me Geraint, by the way. But
Oh, we are so bad at this. It's Geraint. Geraint.
Geraint.
Oh, mate, I'm sorry. We're just going to give you $50 at the end of the show.
Geraint. Okay, Geraint.
Why is it so hard? This must be like some sort of trick that my mind's playing on me.
Can we call you G-Man?
Why not?
G-Man. All right, G-Man.
Okay, so, G-Man, tell us a little bit about your family background.
So I was actually born in Old South Wales. I was raised in the UK. I'm the son of a coal miner, and my mother was an interior decorator. And I'm one of 3 boys, and I'm the only one who does astronomy.
Cool. Really
Sure.
cool.
So, what got you into? What got you motivated into science? Did you love it in school? Did your parents push you to study hard, and it just became? It was astronomy that you studied. How did it all work itself out?
I must admit, I'm not 100% sure. I mean, I was always interested in science as a kid, but just as an interest, it was never something I thought, I wanted to be a scientist. And it wasn't until I was at school and I did my science subject I actually discovered I could do science, I could do maths, etc. And I feel at some level I've sort of stumbled into my career more than anything. There was no grand plan at the start to be a scientist, to be an astronomer. And I didn't know any scientists when I was growing up. I come from a rural coal mining area.
Yeah.
Not really scientists around. So it was more by accident than design.
Yes.
Yeah. Interesting. So, I wanted to talk about a little bit about science in general and the move to popularise science. So you see, obviously, started with maybe Carl Sagan, or obviously Carl was before my time, but the likes of Carl Sagan, now Neil deGrasse Tyson is a very popular figurehead for science. Brian Cox as well in the UK is very, and Europe, or even worldwide is very big. How important is it to get science to the forefront of society and culture?
Well, of course, I think it's very important being a scientist myself.
There's a natural bias there.
There's a natural bias. No, in terms of human endeavour, I think it's very important for people to realise that the world we have around us is the result of scientific inquisition. Inquisition, that's not the right word, but inquiry, scientific inquiry, right. Where people have wondered about how the universe works. And it might take 100 years, but that original thought is turned into the stuff that we just have around us every day. So I think it's very important that we sort of try and bring to the public where we're at now, what it is that we're trying to get our minds around with regards to the universe, and give them some sort of idea where this is possibly likely to take us. Now, another big aspect, of course, is an awful lot of science gets a lot of funding from the taxpayer, and it's it's part of our job to say that this is what your money's been spent on.
Yeah.
Okay, and science is very broad, of course, right? You have everything which people can look at and say, well, that clearly has applicability potentially to me. So you do things like medical imaging and medical diagnostics, but then at the other side, you've got the blue sky science, which is the stuff where people looking at the inside of the very centers of atoms or the forces in the universe, and we don't know where that will take us. But if we're ever going to explore this universe, we're going to definitely need new sources of power, new kinds of materials, and we have to keep looking for them.
100%.
Hey, Geraint, G-Man, I've developed a lot of weird theories and I've heard facts along the way about science, which I do eventually want to speak to you about. But one of the first things I heard about science, and I think it's such a cool way, and one of the reasons why I really love the idea of it so much is a scientist, I can't remember who it was, but basically said we've been given the answer, so we're all here, and we're looking at, a mathematics question on a piece of paper. We've been given the answer, and we're trying to work back step by step until we sort of have the right questions for it. Do you
figure out the equation?
Yeah. Do you look at it like that?
Yes. Yeah. Well, yes and no. So there are two ways of doing it. So you can look at the world around us and just say, how does the world function, and try and pull it apart bit by bit. And this is, this progression we've had in science is, going into the very, very small and into the very, very large to try and work out how the universe operates at some level. But the flip side is also true. Scientists like playing what-if games. And the question is, what if atoms behaved like this? What would the consequence be, and how would I develop an experiment to test my ideas? So we do both. We try and deconstruct, and we try and play what-if games and imagine how, if something has a particular property, what kind of observational consequence would it be? So we're always pushing the two boundaries. So we just don't take the world around us as we see it as a given. We always can think of new experiments to just keep testing the way that the universe works. And so we can play these what-if games continuously as well.
Okay.
So, okay, cool. So why don't you tell us about pandas? Is that how you would pronounce it?
Pandas.
Pandas? Okay, so the Pan-Andromeda Archaeology Survey.
Yes.
So that's
Not the animal native to China.
Not the animal native to China.
Yeah.
That's the solar systems, galaxies?
Galaxies.
The galaxies that are basically our closest neighbours, correct?
Yes.
Yeah, that's right.
Okay. So tell us about what you do there at pandas.
So first thing I should do is apologise in the fact that astronomers desperately try and get, surveys to have cool sounding names. So we have pandas. So
That's a cool name.
That's a cool name.
Everybody loves a panda.
Andromeda is a cool name.
If you ever go to conferences, you'll hear people talking about their work, and you'll hear about wallabies and dingoes and all this kind of stuff, because people have squeezed the acronyms really, really hard. So one of my areas of research is, again, this question, trying to understand the universe we see around us, and how did the universe go from effectively featureless when it was born, it was very smooth and homogeneous, to today where it's very structured. So we have stars, and of course our Earth orbits the sun, and the sun is just one of roughly 300 billion stars in the Milky Way. So that's our galaxy.
Yeah.
So that's a reasonably big galaxy, and then next door to us, cosmologically speaking, at about 2 million light years away, is the Andromeda galaxy.
A stone's throw, basically.
Yes.
Well, we could go a lot further in the universe.
An astronomical stone's throw.
Absolutely.
Bill.
It's considered the local universe.
Yeah.
So this Andromeda galaxy is effectively a mirror image of our own Milky Way. It's very similar size, very similar structure. And so by looking at that galaxy, we hope it can tell us something about our Milky Way. And what PANDAS is, it was a survey done with a telescope in Hawaii called the Canada-France-Hawaii telescope, where we effectively imaged the Andromeda galaxy. Covers a huge amount of sky. If you could see it with your naked eye, it'd be many times larger than the full moon. And if you could see the region that we imaged, it would be an immense portion of the sky. What we were interested in was not the bright disk of the galaxy, which has got its own 400 billion stars in it, but the outer regions. So you have your galaxy itself, and then there's an extended outer region. And we know that outer region contains a lot of this mysterious stuff called dark matter. So the dominant mass in Andromeda is actually material we can't see. It surrounds the optical galaxy. We can't see that, but we can see sort of loose groups of stars which are sitting around in that halo. And so our goal was to image all of that and find all of these groups of stars that are scattered around, which you couldn't see with, in photographic images or with your eye, etc. And the reason we're interested in those bits and pieces of stars that we can see, and there's many, many millions and millions of stars out there, is that they're the leftover remnants from other galaxies that have come too close, and the gravity of Andromeda has grabbed them and pulled them apart. So Andromeda takes these small galaxies, they get too close, gravity pulls them apart, and their stars get mixed in with the stars of
Right.
Andromeda.
Makes
So
sense.
does our galaxy, for example, is ours a strong galaxy that's taken some of what Andromeda has pulled in and split apart? Is that how it works? And
the
dispersed into our galaxy?
No, the Milky Way is doing its own feed-in.
Yes.
So in the southern hemisphere, we can see two galaxies on the sky with our naked eye, the Large and Small Magellanic Clouds. They are two galaxies which are orbiting the Milky Way. They've effectively been captured, and given enough time, they will be consumed. And if our eyes were
Wow.
if our eyes were sensitive enough, when we look towards the galactic center in the constellation of Sagittarius, there's actually something known as the Sagittarius Dwarf Galaxy, which is exceedingly close, exceedingly big on the sky, and is actually being torn apart right now. So our Milky Way is also a feeder of these smaller galaxies. So we know that the big galaxies like the Milky Way have grown over time and continue to grow by, tens of millions to possibly billions of stars in any particular feed-in. And that's what we wanted to see in Andromeda. So we can sort of basically calibrate what it's eating at the moment and see if that agrees with our expectations from how galaxies should evolve.
Now, when you were saying growing, you mean growing in terms of the amount of matter in it, as opposed to growing in size, which would be because of dark matter pushing it away? Is that my understanding?
So it's actually a bit of both. So it grows in terms of mass. So the number of stars continuously increases.
Okay. Yes.
That makes the optical galaxy, the bit we can see, that will actually get bigger and bigger as well. But it's relatively sedate feeding, given the size of Andromeda and the Milky Way at hundreds of billions of stars. When you add another billion, it doesn't make too much of a difference.
For sure.
Yeah.
Now, in roughly 3 billion years, Andromeda will be here. So Andromeda is approaching us at roughly 500,000 kilometers per hour.
Who's got us?
Yeah.
Who's the favourite in the fight between Andromeda and the Milky Way?
Who's your bet on?
All right. So the problem is that they're very equally matched.
Right.
And that is a
good.
disaster for colliding galaxies.
Yeah.
Right? Because if you want, so our Milky Way, which is like a flattened disk, right? It's a spiral galaxy. It's very beautiful. When you look at Andromeda, it's these flattened disks. If it eats a small system, it's fine. Those flattened disks are all fine. But when you take one big disk and another big disk and you crash them together, then everything just gets destroyed. It's all going to be ripped apart. Stars will be thrown out all over the place.
It'd be like two running blades at differing angles coming in and just colliding. Is that how?
Similar, but then remember that the disk that we can see is not a solid object. It's actually made of all these individual stars.
Yes.
So basically, stars just get sprayed everywhere, and they'll all slosh around for about 1 billion years, and then settle down to an object which is going to have roughly 700 billion stars in it, and that's going to be the remnant of these two galaxies that have collided. And it will be rather featureless. The beautiful structures that we see in our own galaxy and in Andromeda will be gone, and there will be this featureless blob of stars left over. And their dark matter halos will have merged around them as well, so there'll be one giant dark matter halo.
So the stars will destroy the planets that surround them, and the stars will be what remain within the two galaxies? Is that how it will work?
So actually, this is one of the weird things, is when two galaxies collide, it's virtually impossible to get two stars to collide, right? So the stars rush past each other because they're all very, very small. Now, the planets attached to those stars are even more tightly bound, so they don't even see the collision. They're perfectly fine. So if our sun is one of the stars that gets ejected and gets thrown out into deep space, it will take the planets with it.
Right.
And we'd have a rather nice view of the collision if that did happen.
It's a best case scenario.
It's a best case scenario, yeah. So, so in about 3 to 4 billion years, our entire local universe is going to change radically because of this big collision.
Right.
It just gives you an amazing insight into how small we are. I know that's a very obviously general thing to say, but I mean to think about how many levels this is going past before you even think about a planet, let alone planet Earth, it's just insane, isn't it?
Yes. So this is one of the things that I find very interesting, is that when you look at the history of science, there's been this step down in our importance in the universe at some level, in that, we used to think that the Earth was the center of the universe. Then we realized it was the sun. The Earth goes around the sun, so maybe the sun is the center of the universe. But then we realized the sun is just part of billions of other stars scattered around. And then you realize that our Milky Way galaxy is one of 100 billion galaxies that we can see in the universe, and each step, takes us further and further away.
Yeah.
What about on a micro level? What about is everything reducible down to a micro atom, and then is there theories that it works the same way on the other end to such a small scale that we can't actually see?
There is at some level, but it stops. Okay. So we can deconstruct and deconstruct and deconstruct, but you cannot deconstruct forever. You eventually hit at the moment. Well, I should clarify that. You hit the limit of our understanding where we have what's known as the fundamental particles.
Sure.
So people might be familiar with the electron, the thing that gives us electricity. You can't chop an electron in half. It's not made of something else. And similarly, when you take an atom and you go to its nucleus, it's made of protons and neutrons. And those protons and neutrons are made of quarks. And what we see so far is you can't chop up quarks.
Yeah, that's what I've heard.
Yeah.
So
That's what I've heard. Me and the boys were talking about this the other day, actually.
over a couple of beers and
Mate, you've been trying to chop up quarks this week? I've been having a tough time.
Johnny said the funniest thing.
So what about going back to what you were saying and extrapolating it further out? What are your thoughts on the multiverse? And for an example, you use that scene from Men in Black. Have you seen the scene where it goes from our planet to our solar system to our galaxy, our universe, and then a bunch of universes, and then that universe is in a marble that a little kid on another planet is playing? Do you believe in the multiverse and that we're...
So the word belief is a dangerous word in science, right?
Okay.
We try not to have belief. We try to have evidence and weigh up the evidence. The problem with the multiverse is that it almost strays into the belief because you cannot get observational evidence. So there are circumstantial arguments that lead people to guess that we are one universe of many. Okay, and in particular, there's this question about the nature of our universe when you look at the fundamental particles and the fundamental forces, gravity, electromagnetism, etc. And they seem to be just right for us to have complex life in the universe. If we change the strength of gravity, or that would change like the lifetime of the universe. If we change the way that the nuclei of atoms work, you can change the rate the stars burn. And it turns out if you do little changes to all of these different things, if the universe had been born slightly differently, then there would be a very high chance that it would be dead and sterile.
Right.
So what people surmise from that is that maybe our universe is just one of an almost infinite sea of universes, and we're in the one where the dice were thrown such that we had just the right conditions for us to be here.
It just that multiverse theory is really interesting, but it's like you said before, it just becomes almost a philosophical idea for which not to go on, because it's just we're just one of tons of universes. It's like, well, what's the point of even just going, trying to look further into that? I don't know.
Because at some level, it does provide some sort of explanation. And now nobody can say if it is the answer to why our universe is the way it is. But it does provide a possibility. But the other thing is that you cannot shut off a direction of inquiry because there's no observational consequences you can think of today, because somebody may think of some tomorrow. Yeah. And there are people that have considered the question of, if you have two universes in the multiverse and they're very close together, can one influence the other? And there are people trying to do experiments which are looking at the way forces act on small scale to see if we could be close to another universe. Now, they're likely to turn up nothing whatsoever. But again, being science, you have to ask those questions.
Yes.
So we can see, as far as my understanding, which is very, very, very minuscule, so we can see with our telescopes back to the start of the Big Bang, right? Because the further you look into space, you can see, obviously, due to the speed of light, you can see where it all began through those particles and so forth. You can find out what was there at the Big Bang. Is that a roundabout?
Is it based on the fact that we can only see 13.9 billion years back, but it could have potentially happened earlier?
Oh, okay. So this takes a little bit of thought to make sure that we get this right. So the Big Bang, when we talk about the Big Bang and the birth of the universe, people often talk about it being, something that exploded.
Something from nothing.
Yeah. But that's not quite the right picture. Okay, so the picture of the Big Bang as we actually know it, how it's described mathematically, is that 13.8 or 9 billion years ago, the universe came into being, okay? And that universe was actually infinite in extent, okay? So stretches for infinity in every direction, okay? And from that initial instant, it's been expanding ever since, and so that means that things have been moving apart. But at all stages, it's been infinitely large. So there wasn't a point that the universe exploded from. It was actually everywhere at the same time.
Wow.
Does that make sense?
This is
Yeah,
very
it does, but it's
interesting.
just so mind-boggling.
Okay.
So mind. So hang on. At t equals 0,
Right.
there was nothing, and then t equals 1 or t equals greater than 0, there was infinity.
Yes. So, but
What does t equals 1 mean?
That's just as in at time. There's no time.
Yep.
And then time is greater than 0. There's
Yep.
plus point 000. Yep.
But can we come back to T equals 0 a
Please,
little bit later?
please,
so,
yes.
so let's just get the picture of the expanding universe correct in our head. So if you think about you've got an infinite universe, everything's expanding away from you, and one of the things that's happening is that there's light traveling through that universe. Now, if you're just consider yourself a dot in that universe, surrounded by other dots all moving away from you, then you can only see the dots from which light has traveled from them to you.
Yes.
Right?
Yes.
So so there are objects out there which are further away than the ones you can see, but you can't see them yet because the light hasn't reached your eye. Okay? So if you imagine our dot, we're sitting at the center of a sphere.
Yes.
And that sphere is defined by the points whose light left 13.9 billion years ago and have reached us today.
Yeah.
That's the observable universe. Okay, so
This has just made the universe so much bigger in my head than what I thought it was. Sorry, please continue.
You think it was just like your mate's backyard or something like that?
Yeah, that's right. Please continue.
Geez, the house is big. It's big as the universe.
That's right.
That's a river.
That's nice. Quite nice.
and so what you've got, of course, is you've got this sphere, and the light that we're receiving now from different objects at different distances set out earlier and earlier as we look back, until we get to around, it's 370,000 years after the Big Bang. That's the light we see in what's known as the cosmic microwave background.
Yep.
Before that, the universe was opaque. So no light could travel in a straight line from before that point to today.
Hence the unobservable universe.
Yes.
That makes sense.
So, but what's happening, of course, is that as time goes on, that sphere we're sitting at the center of just gets larger and larger.
That's right.
And our observable universe gets larger and larger. And so we see more and more of the universe as it goes out there.
That's a beautiful way of, obviously the right way of looking at it. Everyone thinks, okay, there was this huge bang, and then the universe came into being and we were pushed out. But it's actually, from our understanding, what occurred based on the light we're getting now.
Yeah.
That makes sense.
Yes.
Okay.
Yeah. So, if you think of the Big Bang as like an explosion, like a grenade going off, you get the wrong picture of what the Big Bang is.
Yeah.
So,
why is it called the Big Bang then?
So that's actually a very interesting topic. So this involves one of my scientific heroes, who is Fred Hoyle. I don't know if you've heard of Fred Hoyle.
No.
He's considered a bit of a maverick. He had some absolutely superb insight into the universe. He was one of the first people to work out how stars work, how stars turn hydrogen and helium into carbon, oxygen, nitrogen, etc. Now, one of the other things that he did was he didn't actually believe in this Big Bang universe that was born from a starting point and exploded today. So he disparagingly called it the Big Bang in a radio interview. He was meant to be taking the piss a little bit.
Yeah,
right.
And the name stuck.
Yeah, that's really interesting.
So yeah, he
Damn you, Fred.
but I said it's. I actually still think it's a good name. I mean, it was a very
Damn you, Geraint.
it was a very fiery event in the lifetime of our universe. So can we just travel back then to t equals 0?
Please.
Okay, so as we mentioned, we've got this surface around us behind which we can't see light streaming freely because the universe was opaque. And this is when the universe was basically a plasma that we couldn't see through. But we could use the laws of physics to propagate backwards, and we know what was going on and going on and going on. And we can push backwards and backwards and backwards. And we can get to within around 10 to the minus 30 seconds after the Big Bang. We can use particle physics to tell us what was going on, tell us what was going on. And in fact, it's amazingly successful that when we play this all forward, then we actually can predict what elements were made in the Big Bang, how much hydrogen, how much helium, and all this kind of stuff. It works exceedingly well.
Right.
But we then reach this point at around 10 to the minus 30, 10 to the minus 40 seconds, where our laws of physics don't work anymore. We've reached a point in the universe where it's exceedingly dense and exceedingly hot. It's really dense, so gravitational fields are very strong, and it's really hot, and particles are flying around. So we actually have two theories in science, in physics, which we use. One to describe gravity, which is Einstein's general theory of relativity. One to describe particles, which is quantum mechanics. And they don't work together.
That's amazing, isn't it?
So if you have a regime where you have to rely on both, you're stuck because they just do not work together. And so we cannot see what happened at t equals 0.
Yeah, right.
We can't even calculate what happened at t equals 0. So we don't know if the universe was born completely at that point, or if it came from another universe, or what happened. And there's all kinds of ideas that people have, but until we can get quantum mechanics and relativity to play together, we're never going to mathematically be able to calculate through that particular point.
We need that. That's the theory of everything.
That's the theory of everything.
And that's a real paradox that we find ourselves in, isn't it? Because as physicists, which I am not at all, I guess
As equals, as we all sit here as equals. I surmise that.
I theorise that. Yeah, but if the forces of the universe are the same throughout, why don't quantum mechanics and relativity equate? Because if the forces are the same on an atomic level, the forces should be similar to that which they are not, clearly, in a universal or galactic level. Does that make sense?
Yes. The thing is that they do not behave the same way.
Yes.
This is the key thing, is that the universe as it currently operates, gravity dominates the large-scale universe.
Yes.
Okay? And gravity as described by Einstein is all in terms of space-time curvature and all these kind of things that you can read about when you pick up a book of gravity. When you talk about the other forces, there's three other forces in the universe, right? There's the electromagnetic force, which is light. There's the strong nuclear force, which holds the nuclei of atoms together. And then there's the weak nuclear force, which is what's responsible for aspects of radioactivity. When you look at those forces, those are forces where basically little messenger particles are sent between each sort of things. If you have two charged particles, they exchange a photon, and that tells them how to propagate the electromagnetic force. That description of what's going on in terms of quantum mechanics looks nothing like how we talk about gravity in terms of curved spacetime.
Right.
So people have tried to quantize curved spacetime to make it look like what's going on the small scale. And other people have tried to talk about the small scale forces in terms of what goes on with gravity, but they just never, ever work. And, this is not a new problem. I mean, Einstein died in 1955, and on his deathbed, he was working on trying to get electromagnetism to work with gravity.
Wow. Trying to get a square peg in a round hole.
Exactly.
Yeah, that's right.
And we still are.
Can I ask, you mentioned, so at the point, as far as we can see back to T
equals 0. T to about 10 to the minus 30 to the minus 40 seconds.
So 10 to the minus 30, 40 seconds. So that's as far as we can go back, and we have the power to study. So, but you said that people have theories of what happened before that.
Yes.
Can you touch on some of those theories? Because that's the most interesting thing for me.
It's really cool.
I know what we can and have studied and what we do know, but what do people think happened before that?
Okay. So the simplest one is that the universe was really born at that particular point, bang, out of truly nothing, out of no space, no time, nothing before.
Okay, let me hold you up there. Because I truly don't understand how that works.
Yeah, something can come from nothing, which is actually a book that I'm reading at the moment.
That's Krauss's book.
It certainly is.
Yeah.
Yep. Beautiful book.
Yes. So,
Or is that something that we don't know as well?
look again. We don't know, but we do know that quantum mechanics has this random property to it. Okay, so in virtually all of physics as we know it, it's deterministic, right? I.e., if I take an object and I plonk it down, and I come back later on, that object's going to be there. Okay.
Yep.
Now, quantum mechanics is probabilistic, which means that
It'll probably be there.
it'll probably at some level. So let's do a simple example. Imagine you got a box of eggs with one egg in it, right? Now, being classical physics kind of creatures, you have an egg in a thing. You close the egg carton, you open it up. You expect the egg to be in the same hole. In quantum mechanics, what it says is that actually, when you open it up, there's a probability that the egg could be in any of the holes in there, or actually not in the box at all. So things have this probabilistic aspect to them. Now, for big objects like us, those probabilities are tiny, absolutely tiny. But for an electron, they're not. So an electron, so a piece of electricity traveling in a wire, if it is nearby another wire, it can actually, the electron can find itself in the other wire. Okay, it can jump across. Now it doesn't actually physically jump. It just is in one wire and then it's in the other. This is this thing called quantum tunneling.
Sure.
Yeah, and it's basically like teleportation. Basically, there's no rhyme and reason, and it can go between surfaces. Is that correct?
Yeah. Yes.
Like
so
it can go through walls.
It goes through walls.
Yes,
Right.
goes through walls.
So this probabilistic thing means that if you take something like the vacuum, imagine you take a box and you suck out all the air, all the particles, all the light are it, and you've got an empty box. Now, in classical physics, you'd say, yes, that's an empty box. But when you look at the vacuum, okay, in there, in terms of what's going on at the quantum level, you actually end up with particles popping in and out of existence because of this probabilistic aspect.
Right.
So there's this famous thing called the Heisenberg uncertainty principle, which means that you can borrow a little bit of energy for a short amount of time as long as you give it back. You can create a pair of particles and they can exist for a certain amount of time before they disappear again, right? What people have surmised is for the universe, that the universe is just a very long fluctuation. It's borrowed a tiny amount of energy, possibly almost zero energy from whatever, whatever was there before our universe, even if it has no space and no time. And that created the universe. So you didn't need a cause. It's just a fluctuation.
Right.
Yes.
So the probabilistic nature of the universe means that we can't predict accurately, or randomness could have occurred, not randomness, but it could have been just an act of luck that it all started.
Could have been just an act of a fluctuating something.
Yeah.
Now, you have to use the word something because we don't really know what the conditions were like before, but we see that we have this probabilistic aspect in our universe, and we can surmise that whatever was before, that this kind of thing could happen.
So
Right.
could you, using that same analogy of the electron jumping the wire, could you just say that we may truly just be here because an electron jumped the wire and we expanded from that?
You wouldn't need a cause like that.
Okay.
So it could be that there was no space and no time, and that fluctuation produced the space and the time.
Yeah.
Now, exactly what that fluctuation is and what it is fluctuating in, that's all speculation.
Right.
Right? It's just that we know that we can borrow energy in our universe through Heisenberg's uncertainty principle, and it's thought that maybe these fluctuations could give rise to a universe.
Yep.
Now, as I said, these are at some level all speculation.
Sure.
So that one at some level does away with a cause.
Yeah.
But there are other ideas. So that people have is that universes are almost evolutionary, in that imagine that there was a previous universe, and that universe formed stars, and those stars could be very massive. And some of them die, they collapse and produce black holes. So they sort of rip a bit of a tear into space-time. that formation of a black hole in a previous universe created our universe. So our universe has effectively budded off a previous universe.
Yes.
And then in our universe, every time a black hole is created, maybe that is budding off entire universes again from there. So you've got like this sequence that we came from a particular universe and we're going to another universe.
So that's really interesting. This might sound like a really silly question, but so the
No
Big
such
Bang,
thing, Bill. No such thing.
No such thing as a silly question.
Very true.
Just a silly person asking questions.
Well, this might sound like a silly person asking questions, but so if our universe was created through splitting off from a black hole in another universe, and that's the start of our Big Bang. That's where, when you say the Big Bang, that's when, in layman's terms, everything started for us. Okay, so but if that's come from another universe, what are the theories about? I think really deeply sometimes and think there's everything that we don't understand. But there's something so deep that we don't understand, because for me, the fact that we're here, it's impossible that we're here in my mind, because what put the universe there to create the black hole, to split us out and create our Big Bang that started our universe, and the universe that had that black hole,
Yeah.
and it's that revolving.
It's the butterfly effect.
It's the
really.
well, not the butterfly effect.
Well, it's sort of, isn't it?
Well, I'm
Butterfly
talking about like we're chasing our own tails.
Yeah.
Like it's the chicken and the egg effect.
Chicken and the egg.
basically.
Chicken and the egg, yep.
So, what are the smartest astrophysicists and people on the planet think? Why does this happen? Why did it begin? This is the biggest question.
We're asking you what the meaning of the world, the whole universe is.
This is the biggest question in life. But does that make you know? Do you know why it confuses me? Like it's just.
I do. But unfortunately, the answer I'm going to give you is going to be unsatisfactory, because whenever as far as we know, anything that has these kind of processes, you can just keep going back and back and
Absolutely,
back and back.
that's right.
Even if you say, right, we'll stop here, then you've always got the question of, well, what was
That's
before
right.
that?
Yes.
That's right.
We don't know.
Yeah.
It might be just one thing, that it just might be a property of the universe. It might have existed for an infinite amount of time until now. But we just don't know.
Do you think about that?
Yeah, I think about it.
Does it frustrate you as somebody who studies the?
Or does it liberate you?
Frustrate, liberate. This is a tricky. So, as a researcher in cosmology, etc., there is always a lot of other stuff to be getting on with without letting this stop and you doing your day job.
Sulking around. Oh, man.
Yeah.
Still didn't find the start of everything today.
But it is something we sit around and we talk about and etc. But we don't have the answers.
Hey,
And we never will. Let's be honest.
I'd never say never.
I like that.
Yep.
I really like
Okay.
that. Yeah. Hey, you mentioned the big words there, black hole, before. We want to really go into detail about that. We on one of our earlier shows, the first gravitational wavelength was recorded in a black hole, February, I believe, and I believe the second one was just recorded not too long ago. Can you shed some light on, for the listeners and for Bill and myself, on what that actually means and why that is so significant?
Okay, so the story itself has got several parts to it. So we'll talk about the detections first. So what has happened, we'll go back 100 years.
Please.
Einstein working on relativity, studying gravity, has this new picture of gravity where gravity, as I said, talks about the warping of space-time. And what he realized is that when you look at the equations, you can write them down in such a way that the space-time has almost like a springy sort of quality to it, in that if you move something quickly, then that actually puts a ripple into space-time, and that ripple can travel. And if that ripple arrives somewhere and you've got some masses like the Earth and the Moon, then that ripple actually stretches the distance between these guys a tiny bit. What people realized is that you need violent events to set up these ripples. Gravity is the weakest force. So if you want to talk about ripples of any sort of size, then you need violent events. So you need to crash big, massive things together. But still, the signals that would arrive at Earth would be really, really weak. So they've spent the last 50, 60 years developing this new technology to detect these gravitational waves. So what you have is there's two of these detectors, one in Hanford, Washington, and one in Louisiana. And they're telescopes, but they don't look like telescopes. They're actually two metal tubes, each 4 kilometers long. You suck out all the air. You hang masses at either end, and you finally balance the masses, and you bounce lasers up and down the tubes. And then if a gravitational wave comes through, then the length of one tube contracts as the other gets bigger, and then vice versa. Mm-hmm. And the size of that expansion and contraction, okay, now remember this is over 4 kilometers, is about the 1,000th the width of an individual proton.
Yeah.
Okay? So this is why it's taken 50 years to get to this stage.
Yes.
And so the actual first detection was made in September, but September last year, but they published it this year because they do a lot of checks to make sure their results are right.
Yeah.
So what they actually saw is that a wave came through and had a particular kind of waveform. So it oscillated up and down a bit like a sea wave, okay, getting bigger and bigger, and then it gets to a peak and then sort of rings down. So the amplitude gets smaller again, okay? So what they realized is that this wave that they discovered, if you look at it and ask what kind of source produces this wave, the only thing it can be would be a pair of black holes with each with a mass around 30 times the mass of the sun, orbiting each other. Now, as they orbit, because they're releasing these waves, they're losing energy, and their orbits are getting closer and closer and closer, and they eventually crash together, and then they merge. And that merger event is when the two black holes become one black hole. So that's the signature they saw, is the wave going up and down, and then the merger. Now, the shape of the signature, just as you were playing your guitar there, of course, right? You pluck a string and you get a certain wave out. That's based upon the properties of the string. The waveform that they saw basically gave us the most direct evidence that we saw directly what was going on at the surfaces of black holes. So we have black holes in the universe. And this second event that was just recently published is another one which has the right kind of signature to say we've got merging black holes.
Merging black holes. Yeah.
So it's actually very exciting because
it is.
These black holes with a mass of around 30 solar masses are actually kind of hard to make. We know how to make black holes with a mass of around 1 or 2 times the mass of the sun because you can create those from individual stars. We also
So one star dying
yes
is one black hole with about 30 solar mass, did you say?
So one star will give you a black hole of a mass of around 3.
3.
Right? So the question is, how do you get those black holes with a mass of around 3 to all meet each other and build a mass of 30?
Yeah.
Okay, which is tricky. And then how do you get that mass of 30 to meet another one with a mass of 30? So the masses of these guys are a little bit odd, and people are trying to work out where they possibly came from. So it's easy to make really, really big black holes with 1 billion times the mass of the sun. Well, I wouldn't say easy, but relatively easy.
Yep.
And it's relatively easy to make small black holes, but these intermediate masses, they call, are tricky guys.
Right.
So if we start finding that the universe has got a lot of these in there, then there's some mechanism for making that we haven't worked out yet.
Yeah, right.
Which is exciting because it's a new field to study, and it means that there's work to be done.
Yeah.
There's work to be done, yeah.
And that keeps the paycheck coming in.
Yeah, that's right. Now, black holes are really scary things as well, aren't they? Because my understanding of them, which I'm assuming would be a lot of people's understanding of them, would be they're these big sort of self-imploding, masses that have their own gravitational pull or a huge gravitational pull that just go around. Yeah, I look at like Pac-Man.
Yeah,
they just go around and they eat sort of everything in their way. Is there a black hole close to the Milky Way?
Oh, so
or in the Milky Way?
So there are multiple black holes in the Milky Way. So
heart rate's going up.
But you have to be sort of careful with black holes.
Okay.
So they're not Pac-Man.
All right.
Right. So in the middle of our Milky Way galaxy, there's a black hole which has a mass of around, I think it's 10 million or 100 million times the mass of the sun, some number like that. Now it sits there in the middle of the Milky Way, and there are lots of stars whizzing around, orbiting it. And in fact, when you look at the stars, you can measure their orbits over the years, and they look like they're orbiting nothing at all because there's just nothing there. Every so often, a gas cloud will come too close, and as that gas gets caught in the gravitational pull and gets squeezed, it gets hotter, then you get a glow from the center of the galaxy. So that's how we know that the black hole is there. Similarly, scattered through the disk of our Milky Way galaxy, we see individual black holes. And they are eating stuff themselves. But stuff has to get quite close for you to worry about it. They have a very strong gravitational field, but because gravity is weak, you don't really feel them from large distances. It's just like you were traveling past a star. Now, the thing about black holes which makes them scary, in my opinion, is that the gravitational field gets so strong is that once you cross what's known as the event horizon, then you've passed a point of no return.
Yep.
Right? And then once you're inside there, no matter what you do, you cannot get back out again.
Oh, it's amazing.
Right? So if you have a black hole and you fell into a black hole, you could get all the way down to the event horizon. You could possibly climb back out again. But as soon as you've crossed the event horizon, even if you had an enormous rocket pack on your back, if you fired that rocket, then you're going to continue to fall inwards. The gravitational pull is always going to be stronger.
Sure.
And in fact, you actually make it worse because one of the things that happens with strong gravity is that clocks run at different speeds. So you get time dilation, and your time dilation depends upon how deep you are in that gravitational field and how fast you're moving. So if you're firing your rocket to try and get out, you're effectively moving faster and faster and faster, which means that your clock rate actually ticks. Your clock ticks very very slowly compared to everybody else, which means to you fall to the center even faster.
Now, can I try to put that into layman's? Yeah. Can I try to put that into? So, two things. That would look like. So, if I fell into a black hole to you, and so if I fell into a black hole, and I tried to jetpack my way out, you would see me. I would see you getting smaller and smaller and smaller, but you would only see me sort of stop.
Yes.
Because of time dilation.
Well, actually, so the best way to think about this is here, I'm outside the black hole. You're falling inwards. Now, I can only see you because light rays are coming to my eyes,
sure.
Right? As you fall, then the light rays actually have to struggle more and more to get from where you are deep in the gravitational field to my eye. Okay, so there's already a time dilation effect because of that. So I actually see you start to slow, and I also see your light becoming redder and redder and redder because you get this red shifting as you get a larger time dilation effect. Now, as you hit the event horizon, now your photons have to work infinitely hard to get out. So I don't actually see you cross the event horizon. I effectively see your image freeze, and then it goes through red and then into infrared and radio waves, and you disappear.
That is just amazing.
And then once you're inside the event horizon, any light that comes off you can't get out anyway, and it's destined to end up in the center.
So I've just stopped at the point of the event horizon.
So that's in my viewpoint.
Yes,
but to
in your
you,
viewpoint.
you're still going.
Yes. That is amazing, isn't it?
Wow.
And will I always see you? Will there be a point beyond the event horizon where your light isn't able to cross through that path?
No, you will continuously see me. And in fact, what you will see is as you get deeper and deeper is the light from me gets more and more blue shifted.
And that's because your light's getting sucked in to
faster.
the event horizon.
So eventually...
to the black hole.
So you see me in optical light, then ultraviolet, and then X-rays, and then gamma rays. Right?
Wow.
But by then you're at the center, and the gravitational field is so strong that you've just been...
Vaporized.
Well, you get
atomically vaporized.
you get spaghettified first.
Yes.
So-
Yes, because of... Yes, you go.
So spaghettification is that the gravitational pull on your feet is stronger than the gravitational pull on your head, and so you actually get stretched out like a piece of spaghetti.
Yeah,
so
That's amazing.
Yeah. So it
Gumby man.
wouldn't be a pleasant ride.
And is that... you would die?
Yes.
Yeah. Wow. That's amazing.
So I'm going to sum this up. It's probably not smart to fall into a black hole.
Yeah, that's right.
Although there is an out. So if the black hole is rotating, then the structure inside the black hole can be different in that the gravitational field still gets very, very strong, but the point at the center is no longer a single point. It's actually an extended ring. And some people have theorized, guessed, etc., that if you can hit the bullseye and go through that ring, then you might end up emerging in another universe.
Oh, wow.
Right.
But would you be willing to take that bet and jump into a black hole just to see?
Well, if I was stuck flying through space,
I don't have a lot of money.
For some reason, I was stuck just floating through the cosmos. Then I'd be looking for a black hole to get into.
Right, yeah.
Shoot me out the other end.
Yeah, that's a whole lot. Hey,
Hey, before we do, we've got 15 minutes, so I think till we have to be actually driving.
Alrighty, so I wanted to talk about my favourite movie, literally of all time, is Interstellar. Okay, it blew my mind. It's the best thing I've ever seen. And I wanted to talk about what you thought about their theory beyond the event horizon, or what they thought would happen, how he fell through, and then there was a massive sort of time shift, or what, and he could see all different points of time, and it, all these things happened. I wanted to know your thoughts on that.
Okay, so I do like Interstellar, and I've watched a number of science fiction movies over the years which have black holes in them.
Shrek, Avatar.
Well, the key ones for me, you may or may not remember because you're relatively young guys, but in the 1970s, Disney made a movie called The Black Hole.
Okay.
Right? Which you should catch up on. It's a very long movie.
Yeah.
Then there was a movie called Event Horizon.
Yep, I've seen that one. Good movie.
Etc. And of course, Interstellar. And one of the things that these guys have in common is that once you cross the event horizon, then all bets are off, right? Mm-hmm. So in Event Horizon, I think hell was inside the event horizon. In the Disney movie, they fall to the event horizon, and then it just all goes like 1970s bizarre.
Yeah.
Right?
Psychedelic and
disco playing, and everyone's wearing bell bottoms and stuff.
Not sure John Travolta was down there.
Well, you should watch it. You should watch it. It actually has visions of hell, etc.
Oh, wow.
Similarly with Interstellar. Now, so Interstellar basically has this idea that you really mix up space and time to such an extent that you effectively end up in a different time, in a different place, and you can start to play all these kind of games. Mm. Our current theories of black holes basically don't say that you can do that, right? Essentially, if you have a non-rotating black hole, you hit the singularity, squash. If you have a rotating black hole, you might end up in another universe, you might not. But we have a problem again. Remember that I mentioned at the start of the universe, we have strong gravity and we have small scale, and we don't have quantum mechanics and gravity working together. It's probably exactly the same at the center of a black hole. So the center of a black hole, which is thought to be a true point of no size, this thing called a singularity. People think that quantum mechanics actually comes into play and stops that happening, but so some other weird effects will be going on. Similarly, with a rotating black hole, you would have some sort of different structure there to the one we'd expect. Whether or not that allows you to transport yourself to some sort of n-dimensional library in the way that he did and pull on those strings,
fifth dimension.
I don't know if I don't know if that's the case, but we don't know. Okay. I mean, this is any good scientist at some point would just say, look, we don't know. This is where we're at.
Can I ask another really a question asked by a silly person? Can I ask? So, what about would there be a time that we'd be able to send something? You know how we can send stuff to Mars now, and we're sending lots of things to check out other planets around the universe and other parts of the universe or the solar system. Then, is there ever a point where we could send something into a black hole that we could actually document?
It would. I mean, you could drop something in, but once it crosses the event horizon, we have no way of getting the signals from it. Right. So it cannot
because the signal can't get pulled. Can't get out.
So it all gets lost. Yeah. So that really is, as far as we know, it's a one-way street. Now again, there are hints of a way out in that a black hole is curved space-time. So if you could develop a probe that could curve its own space-time around it and sort of protect itself somewhat, it might be able to get out of a black hole. But it's all mights and maybes because we just don't know if that's possible.
The only way to really study a black hole is to get sucked into one yourself, get spaghettified, you'll figure out what's going on, and then you'll be dead.
Well, you'll be satisfied, but then dead.
You'll be very satisfied, yeah. It's like the ultimate safe, isn't it, a black hole?
Yes, well, it's worse than that though, because you wouldn't put your valuables in there because you'd never get them back.
That's right. Yeah. Wow. Yeah. Well, what about white holes?
So white holes are a speculation. So it's one of those interesting things that when you write down the mathematics, okay, mathematics all always reveals more than you think when you first write down the equations. And one of the things they tell you is that you can have white holes, and these are things which expel matter. So you can't put anything into them, but matter can come out. So this is this notion of if you have a black hole in one universe, it could be sort of joined with a white hole in another universe. So this is this idea that people have: you fall into a black hole, but you emerge into a white hole,
Which is therefore called a wormhole?
You can join them with a wormhole in between.
Okay.
A wormhole is a curvature of the space and time in our galaxy, right? To go from point A to point B in the shortcut.
It's an idea.
Yes.
Right? So the idea is that you would basically have a wormhole entrance and a wormhole exit, and they could be separated by any distance, but the actual distance through the tunnel itself could be, 1 meter.
Yeah, that's right.
But again, you can write down equations for these, and they tell you, so to curve space-time, you need to distribute matter and energy the right way. And what you find is whenever you write down the sort of structure for a wormhole and then ask what kind of distribution of mass and energy you need to put in something which has negative energy. Now, negative energy is, it sounds something like from Star Trek, but it's actually something that we know about in our universe. The vacuum itself isn't a source of negative energy. So we know this stuff exists, but we can't harness it. You can't make it, a device out of negative energy. So we can't mine this stuff. So the big question is, if we, how are we ever going to realize a wormhole if we can never put the energy in the right sort of shape? But again, tomorrow somebody might come along, and this is my hope, is that a young person studying physics will come along tomorrow and just have this breakthrough and just realize this is how you create negative energy, and that would open these doors and constructing things like wormholes.
Amazing. I think we are actually going to have to cut our Big Bang and black hole / wormhole chat short today, but I think we're going to have to do this again.
Yeah.
This is just a real taste test. This is the first time we've actually sat down with someone of your stature, G-Man, and it's
mind-boggling.
It's
amazing.
It is mind-boggling stuff. We are obviously on a time. We're budgeted by time with time today, so I think we're going to have to do this again, and you're going to have to tell us about a whole nother realm of physics, because we haven't even touched on dark energy, dark matter, intergalactic space travel. I've got so many questions in here that we could do an extra
time travel,
full 1 hour on, and
full 10 hours on.
Yeah, exactly. So, thanks.
More than happy to. Just let me know.
Yeah,
we can do some more.
Absolutely. Beautiful. Thanks a lot for coming on the show, and that's a wrap. Righto, guys. Hope you enjoyed that. Bit of a mind buster. Brain buster, a bit of a holy shit, did that just happen kind of thing. Me and Tommy loved it. If you guys liked it too, make sure you leave us a rating and a review on iTunes. Give us 5 stars. I asked my friend if she'd give us a review on iTunes. Yeah. She has 4. She's, of course we will. That'd be great. I love the show. She gives 4 stars.
What?
What an idiot.
Oh, as in what?
Because
trying to be realistic.
She said, it's because you told me how you were having all those problems with your equipment in the behind the scenes, and I was like, that was behind the scenes.
Yeah. You don't know about that shit.
Yeah.
Can we mention it?
So give us a 5-star rating review, or don't give us one at all.
Yeah.
Also, though, in all seriousness, guys, there's the show notes on our website, www.adventurefittravel.com/podcast.
Yep.
So anything that we mention in the show that's worth mentioning will be linked in there. So that's all your resources. Also, while you're on the website, join the mailing list so you're up to date with everything.
Bang for buck.
And check out audible.com/ADVF radio for your free audiobook, and www.adventurefittravel for all your cool stuff.
Make sure, guys, it's audibletrial.com/ADVF radio. Audible trial.
That what I said?
I think you said audible.com.
No, I don't think I did.
You sure?
Yeah. You're a flog.
I'm just going to give him a 3-star review.
You're a flog. All right. Thanks.
Bye.
Discovery Roger. Go for deploy.